So you need a high-speed machine vision solution for your high-speed production line. How do you design the fastest machine vision system to match your requirements? Hi, my name is Raghava Kashyapa, CEO of Qualitas Technologies. And in this video, I'm going to break down latency of a machine vision system. So oftentimes, the latency is really driven by your requirements. So if you're, let's say, looking at a very high-speed production line that you would see in maybe FMCG, fast-moving consumer goods, or in high-speed production lines of steel, material is being transported in a very high speed, either individually as parts per second or in terms of a linear speed in terms of meters per second. So we've seen production speeds as high as a few tens meters per second moving across a rolling mill, or we've seen speeds as fast as 1,000 parts per minute in a high-speed bottling line or any kind of consumer good manufacturing company. So if you need to really break down the speed, there are a various number of factors to be considered. The first one is the image acquisition process. So before you even process an image, you need to acquire it. And the question is your camera fast enough to capture an image at that speed that is demanded? And here the question is the frames per second or the frame rate of the camera, is it high enough to be able to image that part? Now, in continuous moving lines, it's the line speed of a line scan camera because you're using a line scan acquisition technique. But if it's a discrete part, then it's the frames per second or the frame rate of an area scan camera that becomes relevant here. So that's the first part. Now the second part is you need to transport that image to the processing system or the PC which is doing the image processing. If you have an embedded system, which is a smart camera or a smart vision system, the embedded compute and the camera are bundled into one device. So there isn't much of a transportation in terms of moving the images to a computational device. But if the two systems are separate, then the interface speed or the communication speed between the camera and the PC is going to come, which is going to be quite important to consider. So, if you're looking at an Ethernet interface, it's as fast as 1,000 megabits per second or a gigabit speed line that you have. But you got to make sure that the transport architecture is well defined. Is your bus interface supporting that gigabit speed that the cable and the camera supports? Is the processor fast enough to be able to acquire those images at that speed? Then moving along, it's the processing time. So the processing time here is how fast will your software take to analyze that image and compute the desired result. So here it's usually the speed of the algorithms that are running and analyzing these images. Now it's typical that higher resolution images will take more time to process, or higher complexity of processing is obviously going to add to the processing time. The last but not the least is then the signal that gets sent to any kind of rejection system or a control system. So you need to make sure that the latency to communicate between the PC or the device that is computing the image processing result and to the device that then receives that signal, be it a high-speed rejection line or be it a robot to go and pick up a part, needs to be then factored in. And that's the communication latency of the control system. So now these are the 4 different latency parameters that you need to factor in, and the sum of all these is going to give you the total latency. Now, if you're designing a high-speed system, you need to break these down into different parts and make sure that the total latency is in alignment with your requirement of takt time. So hope this gave you some information about latency and how you need to consider latency while designing a high-speed line. Thanks and have a great day.